In this example, we're looking at the situation here of having a step shaft. The shaft is fixed to a wall there on the left-hand side at A. It's fixed to a wall there at C on the right hand. There's a rigid coupler B that connects the two, and there's a torque which is acting there at the coupler called TB. What we want to do is determine, as a result of the applied torque TB, what are the torques that are carried by segments 1 and 2, what's the maximum shear stress in each segment of the shaft, and C, what's the angle of rotation there at the coupler B. We're going to begin by drawing some FBDs. As always, I'm going to start out with drawing the free body diagrams of the components, in this case the shafts 1 and 2. So I'm going to show the torques on 1 and 2 as being acting outward like that. So that's really a sign convention. I don't really know that they're acting that way, but I'm going to let math in the end tell me if that is correct. But then what we know then is that the equal and opposite torque then on coupler B will reflect here on the left-hand side T1 as well as the applied torque there of TB. On the right-hand side, the reaction torque there is going to be T2. Our equilibrium equation is going to come from the torque equation for coupler B. That is, I'm going to write down the moment equation. I look back up here and see the X is pointing to the left, so that's going to give me my sign convention on torques too. So there's going to be minus T2 plus T1 plus TB. That is equal to a 0 for equilibrium. Unfortunately, that is the only equilibrium equation that we have. One equation and two unknowns tells us that the problem is indeterminate. That doesn't mean we can't solve it, but what we can't do is just solve for the torques from equilibrium of rigid bodies. What we need to do is look at, in addition to the equilibrium, we need to look at the rotation angles and whatever compatibility equations that we need that come from that. We know that the angle of rotation, delta phi1 for segment 1, is the torque carried by 1 times its length L1 divided by GJ1, where the area, the polar area moment for segment 1 is pi over 2, its radius squared, or to the fourth, so it's d1 over 2 raised to the fourth. And the angle of rotation for segment 2 is T2 L2 divided by GJ2. And the polar area moment for 2, that's pi over 2, times the radius for 2, that's d2 over 2, raised to the fourth power. So this is my equation 2, this is equation 3. What we know is that as we look at how this is constructed here, we know that the rotation at that coupler B, looking at the wall on the right, moving to the left, that's equal to delta phi1. The rotation there, C, is going to be the rotation of B plus the additional rotation there for segment 2. So this becomes delta phi1 plus delta phi2. And where the compatibility comes in is that we know that this angle of rotation at the wall is a 0. So this is equation 4. So that's the 4 equations that we need to solve for our unknowns. Again, because it's an indeterminate problem, we must solve these equations simultaneously rather than sequentially. So for part A, what I'm going to do is grab equations 2, 3, and 4. 2, 3, and 4 are the rotation equations plus our compatibility equations. This becomes T1 L1 divided by G J1. And that's equal to minus T2 L2 divided by G J2. So from this we see that the relationships between T1 and T2 based on compatibility here is minus L2 over L1 times J1 divided by J2 times the torque that's carried by member 2. So this is our second equation. Recall we figured out that things were indeterminate because we had one equation and two unknowns. This is our second equation. We go back to that equation 1, combine that with our equation 5, and we get that torque, applied torque TB equal to T1 minus T2. That means that this on the right-hand side is 1 plus the ratio L2J1 divided by L1J2 times T2. So this gives us one equation and one unknown. We solve the torque that's carried by segment 2. So this becomes minus 1 over 1 plus L2J1 divided by L1J2. That ratio times the applied torque TB. And also T1 therefore becomes L2J1 L1J2 times that same amount here. So it's 1 divided by 1 plus L2J1 divided by L1J2 as that. So we now have the torques carried in shafts 1 and 2. For part B, we want to know the maximum shear stress in elements 1 and 2. So tau max is going to be T1 times the outer radius of 1, so it's D1 over 2 divided by J1. At this point we have everything we need to calculate that. Whereas the maximum shear stress in 2 is T2 times D2 divided by 2, right? Divided by J2. So we have got that. And finally, there for part C, we were asked to find the rotation there at the coupler B. From above, we saw that that's delta phi1. We're now in a position, since we know T1 now, multiply that by L1 divided by GJ1, and we have the angle of rotation for the coupler there for B. So going back over what we did, our equilibrium analysis showed that the problem was indeterminate. We were only able to get one equation for the two unknown torques. Not too surprising because the problem is over constraint. You only need a fixture on one end or the other in order to maintain equilibrium. But we have two. It's over constraint. But that's fine. Then we need to use the rotational compliance of the shaft through our rotation equations, our compatibility equations, to get enough equations to solve for the two torques. Once we have the two torques, we can then calculate the maximum shear stress, as we did there in part B, and the angle of rotation in part C.